Well,
Right.
welcome everyone. I'm especially happy today to introduce Professor Ismaila Dabo from Penn State. Many of you know I am an alum of Penn State. I have a Nittany Lion tattoo on this shoulder right here. That's not quite true, but almost true. I am a Penn State alum, and I'm really doubly delighted to have Ismaila with us today. You know, a couple of weeks ago, actually earlier in this term of our presentations, we had a Eric Miller from the Department of Energy talk about a national program called Hydrogen. And he spoke in a very broad terms about the origin of the program and what it's trying to accomplish. 2 weeks ago, Aziz Asfahani spoke about uh, computational materials design and development. And he spoke largely about metallic materials, but the materials landscape is much more broad than just metals. And in fact, it includes polymers and semiconductors and other types of materials. Today, we're going to hear from Ismaila Dabo, who's going to talk about the work that is being done at Penn State and perhaps other places as well to develop semiconductor photoelectrodes that will allow water to be split into hydrogen and oxygen with electrolytically, but without an electrolytic source other than sunlight, without a power source other than sunlight. So Ismaila, we're delighted to have you with us today, and I'll turn the floor over to you.
Right. Thank you very much, Ron. So good morning, everyone. I'm very happy to be here and contribute to that discussion. In the continuation of the presentation by Eric Miller that you had on the hydrogen program, that is a very large program funded at the level of billions of dollars in order to accelerate the development of the hydrogen economy. The talk I'm going to present today is more on the computational side and how we can use the increasing computational power that we have nowadays to enable the discovery and the development of semiconductors for the production of hydrogen, whether you want to use it as a transportation fuel or whether you want to use it as a chemical feedstock for a number of applications. The work that I'm going to talk about is very collaborative. So you will see that it involves expertise in synthesis at Penn State with the group of Reshak, in the electrochemical characterization with Tito Abunia at Cornell, as well as materials modeling. And so my contribution to that work has been on the modeling side. And so I'm going to discuss why it is important to use models to accelerate the development of those materials and how effective that approach can be. And also, towards the end of the talk, I will discuss validations of those results, validation of the performance of the materials that we propose, using a collaboration and facilities that are available at the National Renewable Energy Lab that really provides a critical feedback to our calculation in order to refine the computational models that we use. So before I jump into the description of this research that was funded by the NSF and the DOE, I'd like to step back for a moment and provide an overview of the framework that we use for this data-driven materials discovery. And so for that, we need materials data. And the framework that we use to predict the properties of material and form those databases is that of quantum mechanics. So I'm going to explain the importance of this equation, the Schrödinger equation, and how it enables us to generate those data that can be used then to guide the choice and the development of specific materials. So to highlight the importance of this equation, so many of you are physics majors and have a background in physics, so a lot of it will be familiar, but I guess for the broader audience, it's still useful to get an understanding of why do we need quantum mechanics at all to study new material. And the answer is because any material is really the combination of nuclei and electrons. So the nuclei are those beads here that you see along this polymer chain. So this is, for example, a polymer material that is used to make plastic solar cells, organic solar cells that are flexible, that are light, and that can convert solar light into electricity. So this is one of those molecules on which we have worked in the past few years. And you see here the electrons that are really this red and blue cloud that surround the nuclei. So without the electron, material will not be stable because nuclei are positive. And if you bring together positive particles, they will just repel. And it's really the electrons that are going to stabilize matter. So without electrons, nothing around us will be stable. Materials will not have the necessary chemical stability to exist. And so electrons are, in fact, the glue between the nuclei. And understanding that glue is very critical to understand the stability of matter and also the interaction of material with light, which is one of the topics I'm going to talk about, because light gets absorbed through the excitation of the electron. And so understanding the behavior of the electron is very important to predict stability and interaction with light that is relevant to the research I'm going to talk about in the next few slides. So electrons are not classical particles, and because of that, we need to go beyond Newton's law and use Schrödinger equation in order to predict the dynamics and the equilibrium state of those electrons. So just to illustrate this equation here, I have here a comparison of Newton's law to Schrödinger equation. So the Schrödinger equation is very much similar to Newton's law. It predicts the dynamics of system, except that instead of having the dynamics of a classical particle, for example, here, if I take an atom of hydrogen with an electron that gravitates around a nucleus, I will not describe this particle as a point, but as a cloud. And this is here a simple simulation that illustrates the outcome of Newton's law. So F equals ma. You simulate this electron, light electron, as a point, and it will just gravitate, forming orbits around the proton in this hydrogen atom. Now, if you switch to the Schrödinger equation, you get a different view. Instead of having this point particle, you get this cloud that evolves according to the principle of quantum mechanics with a spreading of that cloud. So you're more and more uncertain about the position of the particle over time. And you only get a probabilistic vision of the dynamics of this particle. So they describe the behavior of electrons in similar ways, except that in one case, particles within the Newton's law are points, but within the Schrödinger equation, there will be a cloud that gravitates around the nuclei. And so you can not only simulate atoms, but you can also simulate molecules. This is H2. This is the molecule of interest that we're talking about for the energy transition. You can, again, simulate the behavior of that glue as you break apart the molecule. And by solving Schrödinger equation, you can essentially get an idea of the breaking point of that glue. And you can calculate the energy that is released during that breaking chemical reactions. So that Schrödinger equation really helps you understand the strength of the glue. And from that, you can understand and predict the chemical stability of a material. You can calculate the energy that is released upon breaking apart a molecule. You can understand the interaction of light with molecule. You can understand how the absorption of photon is going to excite the electrons and bring them from a low energy level to a higher energy level. And from that, you can calculate the optical properties of materials. And all of that becomes critical when it comes to discovering semiconductor that can absorb solar light and then convert that solar light into sufficient energy to be able to cleave water into hydrogen and oxygen. So this is really the driver of all of this research. How can we use quantum mechanics to accelerate materials development? And I'm going to focus now the discussion about the energy released upon breaking this molecule of H2. It turns out that this molecule of H2 has a very high energy content. When you break apart that H2 molecule and combine the resulting hydrogen with oxygen, you can obtain a large amount of energy that is actually much higher than what you would obtain through the combustion of gasoline. So as a estimate, 1 gram of gasoline contains 50 kilojoules of energy in terms of its combustion energy content, while 1 gram of hydrogen contains 120 kilojoules of energy. And so this becomes very interesting from the point of view of the energy content, the point of view of the energy density and the power density. And the other key advantage of hydrogen is that if you combine it with oxygen, the only byproduct of this reaction is going to be water. So this becomes extremely interesting for the energy transition for the transportation sector. Another use of hydrogen is the conversion of carbon dioxide into synthetic fuels. So you need to go from CO2 to hydrocarbons. And for that, you need to remove the oxygen and separate it from the carbon and combine it with hydrogen. And so for this type of synthesis, hydrogen chemical feedstock become extremely important. Another area where it's very important, it's agriculture. The main fertilizer that is used nowadays to produce fuel is to produce food is ammonia, and the reaction of nitrogen with hydrogen enables you to produce NH3, that is a very important fertilizer for the food industry. Similarly, a use that we don't talk about very often is the extraction of metals. So in metallurgy, you can use hydrogen actually to convert oxides into metal ores. And this is an area where we need, again, a lot of cheap hydrogen feedstock. So I'm going to focus on this application here and this one before talking about the way in which we can generate hydrogen. So this is a graph of the global consumption of gasoline over time. And it is broken down into two contributions that, as you can see, are of a very large magnitude. So we consume every day tens of millions of barrels of gasoline. So this is a consumption that is very impressive. And you can see here that you really have two contributions in this consumption, a great contribution that corresponds to light-duty vehicles. And because of the introduction of hybrid vehicle and plug-in electric vehicle here, you see that this contribution here is almost stable. And this is thanks to the electrification of the light-duty fleet. But what you can see here is that the blue contribution that corresponds to heavy-duty vehicles keeps increasing over time. And this is because it is much more harder to electrify heavy-duty vehicles, because the batteries that we have nowadays do not have the energy content that is sufficient to power those heavy-duty applications. And because of that, hydrogen becomes extremely interesting in order to be a substituent to gasoline for this type of heavy-duty technologies. In the form of fuel cell, you can convert hydrogen into electricity, with water being the only byproduct. Another application that we don't talk about a lot is the use of green hydrogen for the recovery of mining residue. So I take here the example of bauxite that can be converted into alumina using the Bayer process. That is a 6-step process that involves the grinding of the mineral, the digestion, using caustic acid, decantation, producing this residue that is called the red mud, and then precipitation and calcination in order to get alumina. And so the two main byproducts of this are really red mud and alumina. Alumina is the byproduct that you want, but red mud is very much the release, the byproduct that is that can have catastrophic environmental consequences. And this is, for example, the situation that we have in my home country. So my family is from Guinea in West Africa. And Guinea is one of the main producer of bauxite. And you can see here one of the bauxite mines that are in the region of Sengaredi, where all of the red mud is released in the environment. And because this is the product of the digestion in acidic environment of rock, it has catastrophic environmental consequences. And so using hydrogen, we can actually treat that red mud and convert it into more minerals. You can extract from it iron, titanium. You can extract from it critical minerals and rare earth that can then be value-added elements to the extraction process that is obtained by this bioprocess applied to bauxite. So this example really showed the importance of hydrogen. It can be very important for synthetic fuel, for the energy transition in transportation. It is also extremely important for extraction of mineral and also for food production. But the question now is, how do you get that hydrogen? The main process in which hydrogen is obtained right now is by the conversion of methane, natural gas, into H2 using a high temperature process that is called steam reforming. So essentially mix CH4 at high temperature with oxygen. And what you're going to get is H2 and carbon dioxide. And so this process of steam reforming that is very high temperature produces a lot of greenhouse gases. In addition to that, because it's a higher temperature process, you need a lot of energy for this. And because of that, the cost of production becomes extremely large. So there is interest from the point of view of cost and from the point of view of the environmental impact to substitute the steam reforming with alternative ways of production. And there are essentially two ways in which this can be done, and this was probably addressed and discussed by Eric Miller in the previous talk that you had. You can either rely on solar cells plus electrolysis. So essentially, you have a solar panel that converts solar radiation into electricity. Then you have a hydrolytic cell that on one side is going to extract electrons from water to convert water into proton and to oxygen. And on the other side, the protons that have been produced are going to receive the electrons of high energy that are extracted from the solar cell in order to reduce the proton into hydrogen. And so this approach is sustainable, with the caveat that the materials that you typically use for processing and promoting this conversion are platinum group metals that are not earth abundant and that become extremely difficult and whose cost is increasing due to multiple demands across industries. So one way in which you can achieve the same process without having to rely on platinum group metals is through photoelectrolysis. So here we have a semiconductor that typically involves main group metals in oxide or sulfide form. The solar cell is going to absorb the photon. The semiconductor is going to absorb the photon, generating an electron at a high energy level using the energy of the photon. Then, because you have a semiconductor in a solution, you're going to have a depletion layer, an interfacial electric field that is going to drag the electrons to the surface of the semiconductor, where they're going to be able to convert the proton into hydrogen. And on the other side, you have the converse reaction. The holes are going to navigate to the surface, and they're going to convert the water into oxygen and to proton. So this is an alternative to this approach that involves platinum group metals. And this has the key advantage of potentially being amenable to earth-abundant elements. So there has been a lot of techno-economic analysis on this second process on photoelectrolysis. So this is one of the main studies that was done in collaboration with the Department of Energy, where they looked at many different possible technological options for photoelectrolysis. One of the simplest one is this single bed particle suspension reactor, essentially where you have a bag that has nanoparticles or microparticles that is suspended into a solution. And those particles are going to absorb solar light. And upon absorption of that solar light, on one hand, they're going to catalyze the first half reaction, that is the conversion of proton into hydrogen. And on the other side, they're going to take the holes that are going to navigate to the surface and convert the water into oxygen and into proton. So there has been a lot of cost analysis on this type of technology, and it is estimated that the implementation of this type of technological reactor will enable to bring down the cost of hydrogen production from $13 per kilogram of H2 as is obtained from steam reforming to something that will be competitive with the cost of gasoline. And so what is very important if you look at this analysis is really the cost sensitivity. The main driver in the cost of hydrogen is really the efficiency. You can see that depending on an efficiency of 5% to 15%, you can nearly double the price of the hydrogen that is produced. And so it's very important for the practical deployment of this type of technologies to be able to develop sustainable material, earth abundant, that are efficient, that will enable the conversion of solar energy into hydrogen with an efficiency that will at least exceed 10%. And this is where materials, computational materials science, data-driven material discovery becomes extremely interesting. This is a graph that gives a sense of what has been done in the area of data-intensive material discovery using data from quantum mechanics, and now we can use them to accelerate the screening of materials. So this is a graph of the number of publications according to different application areas in the area of data-driven materials discovery. And you can see that there is a lot of vitality and diversity of use of this type of techniques, from battery engineering to the design of solar cell, to the design of optoelectronic material, piezoelectric, dielectric. But what is also very important on this graph is that only a small fraction in orange of those publications in this area of computational material discovery are really validated against experimental data. And so this is, I think, one of the main frontier nowadays. How do you really use these data-driven techniques, combine them with experimental verification to get feedback on the model, refine them, and really have an impact in terms of practical discovery and practical deployment of actual material. And so this is the key graph that really motivates the next step of this collaboration. So we have worked with PIs at Cornell, investigators at Penn State and the National Renewable Energy Lab to develop this data-intensive material discovery cycle in which we have cross-validation between theory and experiment. So I give you here a very high-level view of this discovery process. So the first step is to use computers to solve Schrödinger equation for a wide range of material and essentially determine the strengths of the binding between the nuclei. And from that, get a sense of the stability of the material. Essentially, if you take the material in water, are you going to decompose the material into its constituent, or is it going to be able to be durable under operating conditions? Then we go to the computer, and as I said, you can calculate the energy of electrons, and you can determine the band gap of the material. Essentially, what is the excitation energy of the electron in that material? And this will enable you to determine what are the wavelengths of light that are going to be absorbed by this semiconductor. Then the key question is a question of band alignment. So I told you that upon absorption of light, you have electron and hole that migrate to the surface, but then they need to jump from the surface of the semiconductor to the water environment. And for that, you need the electron, the energy of an electron in the semiconductor to be higher than the energy of an electron in water. And so you need the redox potential of the semiconductor to be higher than the redox potential of water for the reduction of water. And the other side, you want the opposite. You want the energy of an electron in water to be higher than the energy of an electron in the semiconductor. And so for that, you need the redox potential of oxygen of the reduction of the oxidation of water to be higher than the redox potential of the conduction, the valence band of the semiconductor. So once we have done those calculations in the computer, we can then turn to practical consideration of toxicity. You don't want to use elements like lead, arsenic, typically for this type of application. You want the material to be earth abundant. You want to determine whether or not there are synthetic methods that enable you to readily obtain the material in a scalable way. Then we can refine our calculations, applying a higher, more advanced level of quantum mechanics. And once we have done this, then we can recommend new materials, make them in collaboration with our colleagues that are experts in synthetic chemistry, investigate the phase purity of the material using X-ray characterization and the X-ray signature of the material. And from that, we can finally test the photocatalytic activity, and we can learn from this process and iterate the cycle in order to expand the pool of available materials for that conversion of solar energy into water. So I'm going to focus more on the first 3 steps here, and then I'm going to tell you about the validation that we have done in collaborations with Cornell and the National Renewable Energy Lab. So the method that we use is density functional theory. I will give you an overview of the method, emphasizing why it's important for the purpose of material discovery and how we can essentially accelerate those predictions. So the key equation that we want to solve is, again, that Schrödinger equation, H psi equal E psi, that has this object that is the Hamiltonian. It's a many-body object that tries to keep track of all of the interaction between all of the electrons at the same time. And so this turns out to be extremely computationally demanding. Even if you had all of the computers on Earth, you cannot solve the Schrödinger equation for systems that exceed, let's say, 100 electrons. And so this becomes a critical hurdle when it comes to generating data for the discovery of new semiconductors. So instead of this many-body Schrödinger equation, we can simplify this Hamiltonian into a one-body effective Hamiltonian. And the key function of this Hamiltonian is to keep track of the interaction of the electrons with the globality of all of the electrons in the system. So instead of having a pairwise interaction, you look at the interaction in an effective way, looking at the interaction of one electron with all of the electrons together. So essentially the interaction of the orbital of one electron with the charge density of the entire system. And because this effective Hamiltonian is one body and is parameterized by the total density of the system, we call this method density functional theory. Yes.
I just got you synced, and I'm in the middle of something else. Can I call you back shortly? I'll call you back around just after 12. Okay. Okay. Bye.
Let me just interrupt for a moment. If everyone could mute themselves, that would be helpful. Albert.
Right. Mute.
Yeah.
Right. No problem at all.
Sorry.
Actually, it's a good point.
No problem. Okay.
It's a good time to take questions if there are any questions about what I just described. So there is this Schrödinger equation that is the equivalent of Newton's law for quantum electrons. We simplify it by essentially saying we're not interested in the interaction between each pair of electrons, but between an electron and the globality of the charge density. And so this enables you to accelerate the process of solving this equation for systems that have more than, let's say, tens and hundreds of electrons from which you can generate data of band gap chemical stability for the iterative process that I've just described. And so this method has been extremely fruitful in the area of computational material science, computational physics. This is here the mountain of papers that essentially is obtained, if you can read here, by essentially tracking all of the papers that have been ever published in the scientific literature and just printing the first page of those papers. When you stack together all of those first pages, you get a very high stack of papers that is much higher than the Eiffel Tower and almost as high as Kilimanjaro. And you realize that at the very top of this mountain, you have very few papers that have had more than 10,000 citations. So they're on the order of 100, 200 papers that have reached that level. And many of those papers are actually papers about how to solve and simplify the many-body Schrödinger equation. Beyond that, if you look at the top 10 papers, and this, I apologize, this is a bit small, but you will see that most of these papers are about genomics, DNA sequencing, proteinomics. So I would say the first 5 papers, the most cited, are about biology. But then immediately after, you have 2 papers that are directly based on this density functional theory that enable us to essentially fingerprint materials, determine their properties before they are actually made. And so this has been extremely fruitful in the area of material science. And this is the reason why those papers are so cited, because they really provide a computational window into the performance of material. Okay, so this is one metric, and you should really take this with some critical insight, some critical a grain of salt. This is one metric that suggests that this method is important. There are many other important metrics, but at least I think it emphasized that this method is something that cannot be overlooked in the area of computational material science. So this is what we use. We use density functional theory in order then to perform this cycle of material discovery. We have this integrated computational experimental cycle where the first 3 steps are based on DFT. So we use the effective one-body Hamiltonian to calculate the strength of the glue, the chemical stability, the excitations of the electrons, the solar absorption, and the energy of an electron in the semiconductor relative to the energy of the same electron in the surrounding solution. And so going through those steps, we can rapidly go from 70,000 material, so 70,000 oxides, sulfides, phosphides, so different material, different minerals, and determine through those different steps, 8 steps, which one are the most suitable for ultimately serve as photocatalysts for the conversion of water into proton and the conversion of those proton into hydrogen. So this is the general idea of what we're doing using this iterative cycle that is based on the equation of quantum mechanics. And we use that using a lot of supercomputers and a lot of algorithm to be able to accelerate this process. So now I'm going to talk about the experimental verification. This is very much the most interesting part from the practical point of view. Are the materials that we predict consistent with experimental observation? And is the performance that we get from the computer something that correlates well with experimental data? So this is first about the solar absorption. So as you can see, these are powders of the oxides that were synthesized. And you can see they come in different colors, but all in powder form. And what's very important is to check the phase purity of those compounds. And you can see that in that case, we obtain several materials that are labeled here at the top. And we can then, using optical characterization, determine their band gap. And using this parity plot, compare that with the computational gap that is obtained from density functional theory. And what you can see here is that the band gap that we obtain are pretty consistent. So everything lies on this diagonal line, meaning that you have a one-to-one correspondence between the experimental and computed band gap for most of the material that we had. And so we are very happy to see that. But we also have material, if we go further into the analysis, that are not on that trend. And further analysis enable us then to understand the origin of this discrepancy. If you look closely, many of those materials involve manganese, iron, cobalt, so essentially magnetic elements, so elements that are susceptible to develop magnetism. And whenever you have magnetism, you need to go beyond the method that we use here in order to be more specific in the description of magnetic order and the arrangement of the spin of the electrons across the material. So this typically happens for transition metals. And again, here, this does not affect significantly the outcome of our prediction because we're mostly interested in non-platinum group metals. We're not interested so much into transition metal, but more into main group metals, such as indium, such as lead, antimony, and this type of main group oxide. And so this provides a critical feedback that this method can serve well to predict the optical properties of main group oxide, but we need further work if we were to be interested in transition metal oxide. The next comparison is very much the energy level that I discussed previously, the issue of band alignment. So what we would like to do is to be able to determine the energy of an electron in the semiconductor related to the energy of an electron in water. So this is the redox potential of water. The two dashed lines here are the energies of electron in water, and the top and bottom of those bars tell us about the energy range of the electron in the material. And so what you can see here, based on those DFT calculations, those quantum mechanical simulation, is that we predict that those materials will have a suitable band alignment, meaning that the top of the range of energy is above the energy of an electron in water, and the bottom here straddles the lower bound for the energy of an electron in water. And so now the question is, experimentally, what do we get? So we were very fortunate to be able to collaborate with a group at the National Renewable Energy Lab that drop cast the powders that were synthesized into thin film. And based on that, we're able to do photoelectrochemical characterization to determine the range of energy that we have for these material in terms of their absorption of solar light. And you can see that we do fairly well for most of the compound, except for some of them, for example, for this calcium indate, where you see a shift in the energy. And further analysis, again, enables us to refine our model. And it turns out that in that case, it's mostly due to the presence of oxygen vacancies at the surface. So when you have a material that has oxygen vacancies, it tends to be more electropositive. And because of that, the band gap gets shifted up. And as a result of this, we get this disparity between experiment and theory. So this is also something that is very important for us. The feedback being that we also need to take into account the surface termination in order to properly determine the energy levels of the semiconductor when it comes to splitting water into hydrogen. So now comes the most important validation, gas chromatography, that enable us to detect with high sensitivity the generation of hydrogen. And here, our collaborators at Penn State, Dr. Gopalan and his group, have developed a specific setup that involves a closed cycle here. So essentially, there is a mode of operation where you can close you can isolate the reaction cell from the rest of the environment and have a pump that is going to circulate and improve the sensitivity and the collection of hydrogen. And then what is very important is also to have a purging mode, essentially ensuring that between each test, you remove all of the hydrogen and all the residues. And this is achieved through this other mode of operation. So overall, this type of setup enables us to very sensitively and very accurately, without contamination, detects the presence of hydrogen. And we're very happy to see that after that extended effort that lasted about 3 years to develop this type of protocol, we're able to confirm that a large portion of the material that we have proposed were actually photocatalytic, meaning that they will produce hydrogen upon absorption of solar light. So we're very happy of this progress. And now that we have this cycle that is validated and we understand its limitation in terms of accuracy, the modeling of surface defect, we can now iterate and propose many more compounds. So this is a second iteration of the screening protocol that focuses not on oxide, but on sulfide materials. So we can look at sulfide semiconductor. So we identify 3 of them, and they are very interesting transition in their structure from layer structure to something that is much more bulk-like. And you can see that in that case, those materials exhibit hydrogen production at a level that is comparable to some of the reference materials in the field of photocatalysis. So we're very happy of this progress. And so we have now this process that enables us iteratively to expand the range of materials that can be used for photocatalysis. But also can develop a lot of physical understanding and new design strategies to develop photocatalysts. And the key strategy that came out of this study is the fact that we can tune the band edges, the energy levels in semiconductors that are free of transition metals. So essentially, if you look at the materials that we've predicted, many of them are combinations of elements that live on the right of the periodic table, so very electronegative, and elements that live on the left of the periodic table. We're not so surprised to see p-block elements on the left of the periodic table, those orange elements, because those are very much widely used in photovoltaics. Many of the solar absorbers that we have are actually based on sulfide and oxide of indium, tin, lead, antimony, and bismuth. And the reason being is because they're very close to oxygen. And so if you combine electronegative elements together, the band gap that you're going to get is going to be very small, meaning that you're going to be able to absorb solar light. But the problem with those materials is that because they're very electronegative, they don't give away very easily their electrons. And this translates in the fact that their energy levels are very low, meaning that it's very difficult to extract electrons from those materials. And so the materials that we obtain are often ternary oxide of P block and S block. So in a sense, it's not surprising. You want to have S block, very electropositive metals in order to counteract that tendency of the semiconductor to not give away this electron. So as soon as you mix those initial binary oxide with S block element, you see that you have a shift up of the band edges. But we're also surprised because if now you mix S block elements that are very electropositive with these electronegative elements, you might make the material more ionic, more salty, meaning that they're essentially more transparent. And the expectation will be that those materials will not be so good light absorbers. So the question is, why is this the case? How come that we can still absorb solar light? And it all has to do with the distortion that are induced with the size of the cations that we have in the lattice. So to make a long story short, essentially, when you insert S block cation into the mix, they not only enable you to be less electronegative, so they bring up the energies, making you more aligned with the redox potential of water, but also because of the distortion that you have in the structure, you can adjust the band gap. So it's really a win-win situation for us, where we can not only adjust the band edges, but we can do so without necessarily increasing the band gap due to the insertion of those very electropositive elements that make the material more electropositive. And so because of that, we have focused the search on this type of design strategy, where we take elements on the right of the periodic table to make semiconductor with a small band gap, very good at absorbing solar light, and then mix them with elements on the left of the periodic table to be able to adjust their band gap. And doing so, you see we obtain many materials that actually can adjust the band edges in such a way that they will straddle the redox potential of water. So this is the general design strategy that we're applying now with our process in order to really expand the pool of semiconductor. And we feel that there is a lot of room for development of earth-abundant semiconductor using this design strategy to not use platinum group metal, but use main group metal on the left and on the right in suitable amount in order to both tune the band edges and the band gap of the material. And you can see here that using this strategy, we can again have a screening process using quantum mechanics, propose candidates, and many of the candidates that were proposed actually show photo activity upon switching on and off solar light, the current and the photogenerated charges due to the conversion of water into hydrogen gets modulated. So this is one of the latest development on which we're working on in the continuation of the previous work, where we have developed this method based on quantum mechanics in order to accelerate the prediction of materials properties. So with that, I would like to conclude. So I hope I gave you an overview of the use of quantum mechanics and its simplification through density functional theory in order to predict the properties of material before they are made. And this really enables us to interface with experimentalists to not only look at the chemical stability of the material, their solar absorption, their ability to transfer electrons to the surrounding water environment, and look also at the stability in actual operation, and using a feedback loop to gradually narrow down the choice of semiconductors for photocatalysis. So essentially, we're doing what Edison was doing in the search for material for light bulbs, but we're doing that in a computer using fundamental knowledge that is derived from the equation of quantum mechanics. And this enables us to iteratively propose new candidates and broaden the scope of this type of application. So I would like also to thank the funding agency. So all of that has been funded by the DMRF program, that is a very collaborative program that emphasizes interaction between experiment and theory. The DMR program, Division of Material Research at the NSF, and we also benefited critically from funding for the DOE that enabled us to verify the accuracy of our prediction and refine our computational models by integrating our calculation with experimental characterization that is done at the National Renewable Energy Lab in Colorado. I would like also to thank my collaborator at Penn State, Cornell, and all of the students that contributed to this work, Quinn, Kathy, Hugo, Monica, Julian that did work at the interface of experiment and theory, doing both the calculation and then the synthesis of the material, Nicole, Wenan, Megan, Vincent, and Wen. So this is very much collaborative work where the student can not only learn about the computation, the quantum mechanics, but it's very valuable for them also to be able to collaborate at the interface between experiment and theory. So with that, I would like to thank you for your attention. I hope I was not too quick, and I'll be very happy to answer your question. And this is a most recent picture of the group with all of the students that contribute to this work. So thank you very much.
Thank you very much, Ismaila. That was wonderful. I have to say that was really a magnificent presentation. I'd like to, if you could go back to one of your slides. You had a slide that showed computational data design and development. It was sort of an overall slide of the process.
I see.
Yes, that's it.
This one, okay.
I think this really captures the spirit of all of this, and I just want to emphasize for our crew just how important this one slide is in terms of the research and development that follows. And I want to ask a question, Ismaila. People have been able to demonstrate that water may be split by semiconductor photoelectrodes for quite a long time. The problem is that most of those semiconductors are not durable. In other words, while they're splitting water, they're also being degraded themselves. And I noticed that the very first item on this scenario is chemical stability. Does that refer to the chemical stability of the semiconductor that you're developing in the presence of sunlight? Is that the point?
No, this is a great question. This is actually the very, very important. So I kind of alluded it to at the end of the talk.
Yeah.
And this is very much what we're working on right now. So if I may,
sure.
So I talked about the bulk stability in powder form, the air stability. That's what we calculate initially, the band gap, the band alignment, and then there's this aqueous stability.
Okay.
That is, perfect. I didn't talk about it, but it's a great question because it directly brings me to this next step here that shows the stability in aqueous environment of our compound as measured by the energy of decomposition in water. So we call this the redox free energy of decomposition. And there's a very interesting trend that the more a material is transparent, the more stable it is. So as you increase the band gap, making it more transparent, it becomes very stable. So many of the minerals that are transparent, if you put them in water, they will stay there for thousands of years. But many of the minerals that are very colorful, that can absorb solar light are actually not eco-stable. So there's this trade-off that we intrinsically, that emerges from our calculation.
Yeah.
That there is this competition between absorbing solar light and being stable in water. And so that's not good for us, because what absorbs solar light then will decompose and dissolve in water. So one of the strategies, and this is very much a proposal that we submitted last month, we would like to combine those two, essentially having a transparent core that would protect a light absorbing shell.
Yeah.
And the reason why we think we can do that is because the material within the same chemical family, through the distortion of the lattice, we're able to tune the transparency and the stability. So within the same chemical family, you can interface two materials nicely because they will have the same structure, and then ensure that you protect the material against solar photocorrosion. And that's very much the next step along the development of those materials. Right. So I told you about how we can generate many materials, but now how do you practically design structures that would be resistant to corrosion, yes, and at the same time photoactive? Now
that's really brilliant. That's wonderful. Thank you. No, I see some hands up. Let's go to Eddie and we'll continue. Eddie, you're muted. Yeah.
Yes, actually, it's funny you should mention Edison and the tungsten light bulb, because I think there's an interesting classical addition to what you just have been talking about. In fact, your last commentary there is very, on the head of what I've been thinking. Back in the 80s, I did theoretical calculations related to tungsten spheres and cylinders, which have dimensions less than the dimension of the wavelength of light, and I discovered rather classically that you can actually get peak absorptions given those conditions. So if you know the refractive index of your material, you can actually up the absorptivity. And what happens, it seems, is that you get surface waves and bulk waves traveling through these micro structures, which enhance the ability of the material to absorb. So and in fact, you can get as much as, at least with tungsten, something like a 50% plus absorptivity. So I'm just wondering if anyone has actually done work in terms of particle sizes. I think your last comment about it, combining the two materials is very, very interesting. But it would also be very good if there's some understanding as to what particle sizes actually will enhance, and particle distribution sizes would enhance potentially the absorptivity and the efficiency of your process.
Actually, this is a this is a great question as well, and I'm not an expert in that specific area of development, but people have done a lot on plasmonics and how you can essentially have nanoparticles that serve as antenna to enhance the absorption of light. So in this case, you could combine those with those materials, for example, and decorate those nanoparticles with those smaller particles with wavelengths, with length scale that are tuned to match the specific wavelengths that you want to absorb. And those will serve as tiny antennas that will then enhance the absorption of light. So is that what you're referring to? Is that
that's partly what I'm referring to, but I think it's more complex from my theoretical work that I did, because there are certain resonances that seem to occur as a consequence of the refractive index of the material itself, and I can't speak for, combinations of materials. What we were studying were photoelectric effects in tungsten and photofield effects. So in fact, we're applying electric fields and basically shining lasers on the tip to study the photo emission at the surface.
Right.
But what we discovered was during the theoretical work was that there were characteristic resonances as a consequence. And in fact, my calculations seem to be supported by the data. And it was a classical calculation of electromagnetism. But it seemed to work. And, I'd be happy to share that with you if you want.
I would be very, very delighted to read about that tuning. I mean, there's a lot of opportunity in tuning sizes. When you change the size of particle, you can change the curvature and kind of the local bonding environment. You can enhance absorption or desorption. So things that are more curved tend to be more prone to absorb molecules from the environment. There are also effects in terms of the band structure that would be quantum mechanical, and effects that are classical that you mentioned in terms of tuning the resonance wavelengths. So I'll be very interested to learn more, and I think a combination of all of those strategies would be required to really bring that efficiency above 10% threshold for cost effectiveness. So I very much welcome.
Yeah, I've got some old papers I can probably send you, and possibly some unpublished data. But the other thing I was wondering, just very quickly, is potentially to add a third layer, which would enhance the absorptivity. If you can figure out a material like tungsten or encase it in something that makes it extremely stable, then, as you said, for thousands of years.
That would be very, very good. And so if the thickness of the third shell is small enough, it will still be transparent.
Right.
But still provide that protection.
But it makes the photons swirl around, giving you a greater opportunity to potentially absorb it.
I see.
Yeah, that's the kind of weird idea I just had.
Yeah, that's a very interesting idea.
So I put my email in the chat, and I hope I'll receive.
I'll send you some stuff. I'm not sure.
All right, let's go on to Michael. Michael's got his hand up. Michael?
My question is quick. Once you develop the technology, are you anticipating that you can use this with fresh, salt, deionized, distilled water?
That's a very, very important question. So the water that we use there is not fresh water. It's not salt water. It's water that has been treated. And so there's this question as well of the treatment of the water in the cost analysis. So this is something that is part of the life cycle analysis of the technology. And this is something that has been carefully considered in this type of studies that was done a few years ago in collaboration with economists, people that think about life cycle, with chemists and with engineers, and that aspect of the purification of the water is also part of that cost estimate that is here.
Yeah,
that's a very important aspect. And you naively thought that you could produce hydrogen at almost no cost, right? But because of all of those extra treatments and also the end of life rehabilitation of those facilities, you need to also take into account this into the price. So that's an excellent question. It is included. I didn't talk about it, but you cannot do that for the moment with seawater. You need purified water to avoid contamination of the surface of your particle.
Sure.
That's a very good question.
Well, I think LCA is becoming much more focused attention on a lot of these processes. And so I think it'll be interesting to see how that works out. Thank you for your answer.
Yeah, thank you.
Let me just follow this up. I have two questions that I think are very relevant. Number one, the practical approach that you're thinking about then is to use nanoparticles as nanoparticle semiconductors as the device for splitting water. But is that correct? And would that would then eliminate the need for transportation infrastructure to transport hydrogen or liquefied, or how do you envision this going forward?
Yeah, so this is a very good question. So this particle here, so the sphere here would be the semiconductor, and it's actually decorated with some other particles. These are co-catalysts. So those are catalytic materials that will help promote the reaction.
Yeah.
And so there exists earth abundance catalyst. So there's another aspect to this, not only the absorption, but also the promotion of the chemical reaction.
Right.
You need a support for the reaction to proceed. But you will still need hydrogen storage to be able to implement this technology. You can transport hydrogen using pipes, but you have a problem of hydrogen embrittlement. So the hydrogen is very corrosive, and the durability of the transportation infrastructure for hydrogen is still something that is very much at the forefront of the research done by the community, especially funded by the DOE. So yeah, that's a very good question. So the transport is also another issue in the implementation of.
And then one other question to follow up on Michael's. If you're using seawater, well, let me back up. If this is water that is free of contaminants like chloride, for example, you need a semiconductor band gap that will exceed the energy required to split water, 1.25 volts, something like that.
Yes.
So the band gap energy required to split to produce chlorine would be a different band. I think it's more like 1.6 volts or something like that.
Yes.
Could you tune by tuning the semiconductor microparticle or nanoparticle, could you tune it so that it would split water to produce hydrogen, but would not produce chlorine, for example?
Yeah. This is a very interesting thought, and actually there is a lot of studies also about the use of similar process.
Yeah.
Band gap that are adjusted to other reaction to remove contaminant from water. So you can also do photocatalytic wastewater treatment. You can selectively reduce different compounds, the different elements, and this can be at the upstream of this process. Before that, you can use maybe photocatalytic purification, and then use the water that comes out of it to then be transformed with lower band gap material. So you can have a cascade of materials of increasing lower band gap.
Yeah.
You react with chlorine, and so you will use a large band gap material, and then as you get to the 1 volt and 1.23 volt, you can then focus the attention on the conversion of hydrogen into hydrogen, of water into hydrogen. So that's a possibility. I'm not an expert in water treatment, I have to say, but I've collaborated with laboratories in Japan on the specific question of using photocatalysis to purify water.
Yeah.
So that could be
one of the thoughts that has occurred. One of the things that occurred to me over the years is that, if water splitting using semiconductor photoelectrodes were coupled with desalination phenomena, desalination process, you could then imagine providing an energy source for the planet that is free of geopolitical boundaries, free of international disputes, because you could desalinate, which is done in the Middle East. Desalination is common in the Middle East as a matter of providing potable water. You desalinate the water, then you could use semiconductor photoelectrodes to split it to produce hydrogen and oxygen. And, there's a lot of steps between that and going to a practical energy medium like hydrogen. But nevertheless, it could be done. it's not impossible to do this. It could be done. And I keep thinking that, you know, it would eliminate the need for infrastructure, and in many respects, it would eliminate disputes among nations. It would be an energy source for legacy and non-legacy nations. It would be really important if we could do that.
Yeah, I totally agree. And the focus of my talk was on photoelectrolysis, and I mentioned also photovoltaics and electrolyzers. I also think this is a very important area of development. So the two are not incompatible. So there are several solutions that need to be applied, and in addition to that desalination solution, all of it, I think the remaining theme is that they all use solar energy as main energy source. But I think there's a lot of possible design and strategies that you can think of around those different options.
Let's see, Wayne, you had a comment.
I just wondered, you may know this already, and I don't think it's, they don't use solar energy, but submarines use hydrolysis of seawater to generate oxygen.
Mm.
Yeah, that's right. That's a good point.
I used to have a fellow who worked for me who was in the Navy on submarines, who told me that. Also, when you showed your picture of, when you talked about transportation and you showed trucks, I thought maybe you were referring to using hydrogen fuel cells instead of lithium-ion batteries.
Yeah.
Was that what you, that's
So that part of the talk, I was probably a bit shy. I didn't explain very well that part, but yes, indeed. So these are fuel cells that can be used to break apart those halogen, steal electrons from the hydrogen molecule, and then use that as energy source. Absolutely, yes.
Yeah, because you know, all the talk now of EVs focuses mainly, at least in this country, on lithium-ion battery, and there's a lot of externalities associated with it. There's big debates now. They found some lithium mine in Maine, and there's big debates about the environmental effects of mining the lithium in Maine, and also there is going to be issues with disposing of the batteries. Only a very small fraction of people drive electric vehicles now. Yeah. And when they're all driving electric vehicles, unless they figure out a way to recycle the batteries, there's going to be a lot of landfills. You don't get that with cars that are powered by hydrogen fuel cells, although they're less efficient. And just a simple side of how much these EVs, how much increased weight the batteries add. I was having breakfast with my wife, and I went outside in the parking lot. There was an Audi electric SUV, and you wouldn't believe the size of the calipers on the front brakes. Those cars are very heavy compared to cars that even have an internal combustion engine in them.
Yeah, absolutely. Yeah, the power density and the energy density is on a mass equivalent is not sufficient, and that's why the bigger you go, the more power you need, the bigger those systems become. And by the time you reach a truck, for a transportation truck, then it becomes impractical. So yeah, I can totally agree with that. I would say that there's a lot of work, in particular at Penn State, on the recycling of batteries and all of understanding the life cycle of those battery technologies. And
the charging time. There's a lot of work being done on that. If it takes about the same, a car can drive about the same distance on a tank of gas as it can before batteries need to be recharged, and it takes 10 times as long to recharge the batteries as it does to fill your gas tank. You'll need 10 times as many charging stations as gas pumps that we have now, and this is a lot of change to infrastructure.
Absolutely, yes. And one of the advantages of fuel cell is that a priori you should be able to fill directly your tank with hydrogen in the same way as you will do for gasoline. So there are a lot of trade-offs in the practical use of those technologies. I very much appreciate your comment, indeed.
Can I just interject something here?
Go ahead.
Massachusetts is the first state in the country to name a cabinet level position of climate chief. They just named Melissa Hoffer as our climate chief in Massachusetts here. We were having a discussion with Melissa the other night, and hydrogen came up. And just from her point of view, the use of hydrogen as a transportation fuel is very low on the priority list here in Massachusetts because of the issues of transport and metal embrittlement, pressures that you have to pressurize the carbon, the weight of the tanks, etc. Their view is that hydrogen will be best served as providing power directly into the grid.
Yep.
And I think from your point of view, that might make your job easier too, to have stationary locations producing vast amounts of hydrogen with an insatiable customer, the grid, rather than trying to figure out how to get these things into automobiles and trucks.
You know, I'm glad to hear about that, Michael. I wasn't aware of the conversation, but I think it's encouraging to me to think that people at the state level are thinking seriously about hydrogen.
Very much so. And she's quite brilliant, actually.
Yeah. Well, you know, Ismaila, I promised we'd finish by noon, and it's just about noon. So I do want to bring this to a close. Eddie, did you have a comment? Your hand is up, or is that from earlier? You're muted, Ed.
Yeah, my only comment was that in apparently Canada is also a potential source of lithium, and they would be doing work on the Canadian Shield, which I suspect would be more environmentally acceptable. But there are a lot of places to get materials. The only question is accessibility.
Yeah.
Great.
Well, all right. Let me then bring this session to a close. And I just want to make the observation, Ismaila, I know that you have an undergraduate degree from École Polytechnique in France in mechanical engineering.
Yes.
I noticed that you transitioned to electrochemistry, given your experience at MIT with Nicola Marzani. I really am very happy to have you talk with us today. I think, the young guys like you represent the future of this country. You really do. And the work you're doing is just magnificent. It really is. And you have my loudest applause for the stuff you're doing. I can't wait to visit Penn State to see your lab, but thank you very much for joining us today.
Thank you so much.
Thank you, folks.
I very much appreciated your thoughtful feedback and being kind enough to invite me.
You're welcome.
Very impressive.
Thanks very much, everyone. Take care.
Excellent
We'll see you in 2 weeks.
Thank you.
Thank you.
Bye, everybody.
Bye-bye.
Bye.